Statistics play an important role in genetics. For instance, statistics prove that the number of offspring is an inherited trait. If your parents didn't have any kids, odds are you won't either. You get it? Anyways, so we're going to go ahead and do confidence intervals for means. And let's go ahead and revisit the sampling distribution. So here I have a population that's normal. I'm going to take a sample of 2 and look at the average. And you can see there's 2, there's the average, there's 2, there's the average. And when I take these samples where the average is landing, so this is the sampling distribution down here, they're landing pretty much with the same mean as the population above. All right, so it looks like the original population distribution, which is pretty normally distributed here, but maybe a little less variance. The standard deviation is lower. All right. So let's go ahead and look at a larger sample size of 10. So here comes our sample and our average drops there. Now you're probably going to say, why don't I have any dropping over here or on the right? And the reason is, what's the probability I'm going to get all the 10 of these on the left side or the right side? It's rather low, actually. So you tend to have much tighter distribution with sample size 10, and with 25, it's going to be even tighter because the probability of me even getting all of them in this area, even if I go with a wider area, is pretty low. You can see it's hard for me to miss it. And as I increase the sample size, the distribution looks normal and the spread is narrower. So if you draw the different distributions, you can see again, the first one looks a lot like the original population when I had sample size 2. The second one is much narrower, and sample size 25 was even more narrow. All right. Now, we had already visited this distribution before. It's on your formula chart where mu of x bar is mu, and sigma of x is your sigma for your population divided by your square root of n. When can we use this? When the following conditions are met. When the population is approximately normal, when the random condition is met, that is, the data come from a well-designed random sample or randomized experiment. And remember that the goal is to be representative. So if they tell you that it's representative, then you're fine. 10% condition, when you're sampling without replacement, do not take more than 10% of the population. Now, that was if the parent was normally distributed. What if we have distributions that are not normal? So here I have a uniform distribution, and you can see, will my sample or my sampling distribution for my means, for my averages on bottom, look like my population? And you can see that actually I am getting sort of a center there. And these are sample sizes of 5 and 25. And if I go more and more, I actually have a normal distribution. And when I get even bigger sample sizes, this is 25 here, it's going to be even more normal. So I'll go ahead and start this one on the right, which is for a bimodal distribution. It's sort of bimodal. It's really strange looking. So I tried to make the strangest distribution I could. And if I'm doing sample size 2, you can see that it's possible to get 2 on the left here and 2 on the right here, and you can get 1 of each. And so you get this weird trimodal peak. And then if I go to larger sample sizes, I can get weird things. So this is with a sample size of 5, all right? And I can go even larger sample sizes. Let's do 10 now and see what I start to get. And it's starting to get a little bit normal. Let's go sample size 25. And that takes, so you're going to definitely have more of an average in the center there. And you can see here, as I go and increase the sample size, I am starting to get a normal distribution. So, oop, so what if the population is not normal? Well, if you go large enough sample sizes, uh, you're going to get a normal distribution, which leads us to the following condition. Basically, the large normal sample condition. If n is greater than or equal to 30, or the population is approximately normal, so either one of these works, then you can use the formulas on the math chart, and we can do our confidence interval. Now, remember to check these by making a histogram and or box plot of the sample data. Well, what if we don't know the population standard deviation? So we can still calculate S of x. We're going to need a sample, and the standard error for the sample seems to work well enough, even though S of x is a statistic and varies from sample to sample. So this formula, it looks a little different from your math chart because this is coming from a sample, all right? But they noticed more problems when n wasn't very big, because remember, the condition I just stated was that, even with the small n's, they're still messing up. So that extra variation is an issue. So we'll introduce you to William Gossett. He was a quality control engineer at Guinness Brewer, so he had to sample the beer. And he used samples of 3 or 4 when testing stout, which don't want to drink too much, obviously. And the alpha was 0.05, so he expected to reject about 5% of the good batches. But after further testing, he realized he was rejecting 15% of good batches. Such a waste. All right. So for small degrees of freedom, the shape of the model changes, all right, because he's only doing sample size of 3 or 4. So he had a new model called the t-distribution by simulation. And he actually, this is way back, what's turn of the century. He figured out the exact formula and published under a different name, which is called the student's t-distribution. So what does that look like? So this applet here shows a student's t-curve. When you have a lot of degrees of freedom, notice 40s on our high end here, they look about the same. But as our degrees of freedom goes down, you can see that it gets wider, all right? So you can see the gap. This is the fatter tails, all right? So we have a different curve for every degree of freedom. When DF is small, our degrees of freedom is small, then the tails are fatter, our margins of error are bigger, our confidence intervals are wider, and our p-values are a bit larger.